In this module, we're going to look at the difference between spontaneous and non-spontaneous processes. Our objective is to understand the definitions of both spontaneous and non-spontaneous, and to be able to predict the spontaneity of simple processes. Some topics that we've previously learned that we're going to bring back into the thermodynamics chapter are kinetics, talking about how fast or slow a reaction goes, equilibrium, how far the reaction proceeds toward the formation of products, and enthalpy, the measure of the change in heat or energy that our system has. It's important to understand the relationships between these items and thermodynamic values, but it's also important to understand when they are not related. A common misconception is that spontaneity and speed are related. However, this is not true. Spontaneity tells us whether a reaction will happen or not with outside intervention. Speed tells us how fast or slow a reaction will actually happen. These two things are not related to one another. We can have a spontaneous reaction that happens very quickly, or a spontaneous reaction that happens very slowly. Likewise for non-spontaneous processes. So the question we asked in the previous module was, will enthalpy predict spontaneity? To determine this, we have to answer the questions. Are all exothermic reactions spontaneous? The answer is no. There are exothermic reactions that are non-spontaneous. The next question is, are all endothermic reactions non-spontaneous? This is also no. There are endothermic reactions that are spontaneous. Therefore, enthalpy alone does not predict spontaneity. We need some other value, some other information that will allow us to predict the spontaneity of a particular reaction. So what do we mean by spontaneous? This means the reaction happens alone with outside intervention. If I take a car and leave it outside for many years, I'm going to see that the car is going to rust. This is a spontaneous process. It may not happen very quickly, but it will happen. It's spontaneous. The reverse of this reaction is non-spontaneous. A car will not go from being rusty to being in perfect condition. That is a non-spontaneous process. We can look at other examples by looking, for example, at the ball at the top of the slide. If I let go of this, it's going to roll down the slide. This is a spontaneous process. No outside intervention is needed. However, if I want to go from the bottom of the slide to the top of the slide, that will be a non-spontaneous process. Some outside intervention will have to happen in order to get the ball from the bottom up to the top of the slide. The driving force in this process is entropy. Entropy is a measure of the disorder, or we can think about it as a number of ways to arrange particles. If I look at the potential energy of the ball at the top of the slide, we see that the potential energy is stored there based on the position. If I roll the ball down the slide, my potential energy is converted to kinetic energy. I lose a little bit through heat from friction, and as a result, I'm dispersing that energy. Therefore, it's entropy that drives this reaction from the ball going at the top of the slide to the bottom. If we're lifting a block, we see that it has potential energy based only on its position. If I were to let go of the rope or cut the rope, what we're going to see is that the block will fall. That's the direction of spontaneous change, because I'm dispersing energy as that potential energy is converted to kinetic energy and heat through any friction that may occur. A similar argument can be made for a chemical compound. It has chemical potential. The bonds that are holding the atoms together have potential energy stored in them. As we add this KBr salt to water, what we see is that there is a spontaneous change. We go from the molecule, from the ions being attracted to one another in this compound, to having the ions separated by one another. There are more ways to arrange the ions in the aqueous solution than there are in the solid crystal. Therefore, we're increasing the entropy, we're increasing this disorder, and that is the direction of spontaneous change, going from the ionic salt to the aqueous dissolved ions. So as the commercial goes, diamonds are forever. But are they really? Well, not exactly. The process to convert carbon in the diamond form to carbon in the graphite form is a spontaneous process. It will happen with outside intervention. Thankfully, for the jewelry industry that is, it happens at a very slow rate, such that that ring passed down from generations is still going to be around for several more generations. We are not going to notice an appreciable change in a diamond over our lifetime. When we look at reversibility, what we see is that spontaneous processes are irreversible. It's only going to proceed in one direction, the direction in which it is spontaneous. However, if a process is spontaneous in one direction, it must be non-spontaneous in the opposite direction. This is similar to what we looked at for enthalpy. If we had a positive value of enthalpy in the forward direction, then we knew that the enthalpy in the reverse direction would be negative or less than 0. We looked at many reversible processes when we talked about the chapters on equilibrium. A reversible process will proceed back and forth, so from the forward. A reversible process, we've looked at many reversible processes when we talked about equilibrium. A reversible process will proceed back and forth, so in the forward direction and in the reverse direction. Any reversible process is at equilibrium. Let's look at an example. Given the reaction A in equilibrium with B, which one of the following is true? A is the only possible answer. If the forward reaction is spontaneous, the reverse reaction is non-spontaneous. If we look at B, it says the forward is spontaneous and the reverse is spontaneous. This can't be true because if a reaction is spontaneous in one direction, it must be non-spontaneous in the reverse direction. If the forward reaction is spontaneous, the spontaneity of the reverse reaction is unknown. This is also untrue. We know that if a reaction is spontaneous in the forward direction, it must be non-spontaneous in the reverse direction. Next, we'll look at the second law of thermodynamics.